So the thing is, let's talk about now. Okay, fine. You can write different algorithms now. How to find out that? How to analyze that? The algorithm, which one from among the, let's say, for example, I have given a problem to solve to 10 of you. Okay, I've selected randomly some 10 students and I have told you to solve a given problem, right? Now what happens is, it's your thinking are different. 10 of you will develop different ways to solve the problem. Let's say like I want you to this thing. You are given your marks and then I want them to I want you to find out that who's the most weakest, okay, person among the 10 of them. So you will go on finding, you will do some kind of sorting and all. So you may design that algorithm. Okay, you may have your own idea and you may develop your own algorithm, but I want to find out which one will perform the best, okay, when it comes to real execution and all. Real execution in the sense that, now if we talk of computers, what happens is you have something called memory, right? Then there is execution time. So this all has to be analyzed, right? So the thing what happens is, now mostly like the important thing is like time. Okay, how long it may take to run a particular program. So the thing is, we have 10 different algorithms. We will try to find out, because here there is no way of exactly measuring the time taken, because here we are talking about developing an algorithm. We still not have gone to writing a program. Okay, so the thing is, we just have to analyze. Okay, so now our main aim in algorithm courses, you have to develop an algorithm, then you have to analyze different algorithms. Okay, and you should be able in this subject that you can find out which algorithm will perform best in the problem that is that in the problem that you have to solve. Understood? So we have to analyze space, and mainly space and time complexity. Now space doesn't play that much importance in nowadays, because we know that technology have developed so much that space constant doesn't take that much importance. Okay, but time complexity is really important. Now as you and see on the screen that we will see some definitions, and after that we will see how the space complexity and time complexity can be analyzed for different algorithms. After that only you can find out the best algorithm. Okay, so space and time complexity. The space complexity of an algorithm. Can anyone having this thing, connectivity problem? Student, can you hear me?
Yes, ma'am.
Yes,
Okay,
ma'am.
fine. So the space, okay, space complexity. Okay, the space complexity of an algorithm is the amount of memory it needs to run to completion. Okay, that is what is space complexity. Now we will see like how we can. It's all about analyzing. It's about estimating. It's not about correct. It's not about calculating the exact thing that is possible, because that concerns the architecture of the computer, everything. Okay, that we don't know. We assume that we don't have any idea of that. Then we will see which algorithm will be the same particular problem in concern. Then the time complexity of an algorithm is the amount of computer time it needs to run to completion. Students, here I am teaching you from the PDF. This is from Horowitz Sahani book that I've already uploaded on the Google Classroom. Now here these are my notes. As you can see, these are the notes that I've also uploaded. here the thing is how I have written down the notes is I have just written down that is the important points. Okay, right? As you can see, so you can just go both. You can study both and compare, and you can go through other books also. Fine. This is how it is. Now space complexity here algorithm. There is one very simple algorithm. We will talk about this thing comparing the space complexities of different algorithms. Here, I want to tell you one more thing is that performance evaluation. Now we are talking about performance evaluation of an algorithm, okay? Which are like can be divided into two phases. Now, first one is a priori estimates. This is what the space and time complexity analysis is. It means that these are just estimates. We really don't know how much really space will be taken, how much time will be taken. Sorry, but we have to find out a way to estimate the space and time complexity. Understood? Now this is second is a posteriori testing. This is where the exact performance measurement happens. In the sense that if you are now after choosing the best algorithm, you'll go for programming. Now in that we have many ways of uh, what is that measuring the time taken to execute the program, to run that program. That is the running time. Okay, those are known as a posterior testing. Now again we refer this as first one as performance analysis and the second is performance measurement. Okay, fine. Let's come to specs complexity, which I have like already defined. Now see this very simple algorithm. Okay, now the space needed by this algorithm. Now I am talking about estimates here. So what happens is, see, the space complexity analysis consists of two important components. For okay, the first thing is a fixed path. I will tell you about characteristics, instance characteristics of an algorithm. Now, instance characteristics means that in a particular algorithm, the variables that are in the algorithm. Okay, for example, in the function, you will have some local variables, right? Though, so that algorithm, the space needed in the algorithm will depend on those local variables. Understood? Now here there is another part which is known as the fixed part that doesn't depend on the local variables or input, okay, size of the input, those kind of things. That is a fixed part that is independent of the characteristics. Characteristics means that instance characteristics, that is number, size of the input output. Understood? Now, this part actually what happens is, can you really tell about how much instruction space will be taken by the code written by you? Okay, so those kind of things that it's not in our hand. Okay, those are controlled by the compiler, the operating system. Understood? So we are talking about estimating. Okay, it is priori estimate. So here, what we have in control is the variable that is there in your algorithm, right? So those kind of things and space for simple variables, fixed component variables, these are not, and space for constant, these are not in our hand. Okay. Now second part is a variable part that consists of the space needed by the component variables whose size is dependent on the particular problem instance being solved. Understood? That is the space, the reference variables, the recursion state. Okay, this all depend on the instant characteristics. Now, can anyone tell me if you are solving a recursive algorithm, if there is no base condition, how will the program terminate? Can any one of you tell me that? Have you heard of recursion stack? The recursion stack, it works on which, can anyone tell me what is recursion stack? And can anyone tell me on which principle your recursive algorithm works? Data structure, it's related to data structure.
Ma'am, recursion works on the stack.
Yeah, stack. Stack works on which principle?
Ma'am,
Last
last
in,
in,
first
first out.
out.
Okay, fine. We will see that. Okay, we'll see something related to recursion now. So here, the space requirement, if you define it, okay, the space requirement, if you define it, my dear students, we have already defined first one, that is the fixed part, second is the variable part. So if you, in totality, if we consider the space complexity, okay, of a program S of P, which is nothing but the sum of the constant part and the SP, that is the instance characteristics. Can anyone, is anyone having any problem? Okay, fine. See, this is the algorithm. This is the algorithm that we have just seen on the PDF. Now it is written point-wise. Now let us consider the space complexity. That is, now space complexity we will consider only S of P. Sorry, S of P is nothing but SP. Sorry, it will, we will consider only the instance characteristics because we don't have any idea about when you write a code like how much space your instruction space will take finally when it is compiled, okay, and put in the memory. So now there's a simple algorithm, and my dear students, I want to tell you one more thing. See, this is one way of writing an algorithm, which this particular author has written. Now when you go through a lot of books, you'll see that there are different ways of writing algorithms. There is no specific way that an algorithm has to be written like this. Yes, but when you see the algorithm, it will be much similar to the programming languages that you have learned. Okay. Now here, when you write a simple algorithm, what's happened is they have used keyword and you have the algorithm name and the parameters, right? So here, let us see an iterative algorithm. Now, algorithm are of two types. One is iterative and the other thing is recursive. Fine. Now let us talk about this iterative algorithm sum and let us analyze how much space, that is the instance characteristic related to instance characteristic, how it will take, how much space it will take. Okay. Now here what it says an array has been passed on and it has n number of numbers. Now we're just summing up the arrays. Now how much like memory will be needed? Okay. Now here what happens is, as you can see, you have a variable called s. What is the s? That is nothing but it will have the final result of this sum, right? So you have initialized that into zero. This you know it very well. Here, let us assume that okay, it has been analyzed to zero point 0.0. So let us assume that it is a floating type number. So that data type is, what is that? Float. Now, if I talk of I, okay, I is the index of which is used to control the for loop. So it goes from 1 to n. Here, my dear students, why 1 to n is, it has been just assumed that the array index starts from 1 and it goes till n. Instead of in C, like it starts from 0 and goes till n minus 1. Right? Now, here, the I is of integer type. Right or wrong? The I is of integer type. N will be again storing the number of elements, so it will be of integer type. So in order to simplify, okay, let us say that S takes one word of memory. Yes, it does. It does in floating data type and integer data type according to the compiler. It has different number of words. Okay, so S, if it is of floating data type, it may take 4 in some operating system. Okay, and I integer, it may just take 2. But in order to simplify the whole thing, let us say that it takes only one word. S for S, a space memory of one word, I, a space memory for one word, N, a space memory for one word. Understood? Then here what we have is we have something called inside the for loop, that is some where the sum is being done. You are accessing the S, they just immediate value. Then we have A of I, that is the array elements are, what is that? X is 1 by 1, 1 by 1. So the array here in the algorithm, which looks like a function, right? Which looks like a function in C. So here, as you can see here, local copies of S has been made, meaning that a storage word of memory of S is required for this particular algorithm. I is required, N is required, for array A is also required. That means that these are the instance which are needed. So the instant characteristic of this sum algorithm is made up of, what is that? This variables in the particular algorithm. So finally, can I say that one word of S is required, one word of I is required, one word of N is required, and to store the whole array N. So for array N, how many words will be required? Can anyone tell me? And if any confusion, kindly ask at the chat box so directly you can interact with me. Anyone having confusion, can anyone tell me how many words will be required for the array A? Can I say that n words will be required to store n numbers? So finally, so I have here about one word for S, one word for I, one word for N, and n words for the whole array. So can I say that 3 plus n words will be the space required for solving this particular algorithm? Now, what you can do is, if this S is of floating data type, you can just multiply over here how many, how many words are required. So let's say, like for example, 4 words for floating data type, you can put 1 into 4. If integer 1 into 2, that is the thing. Simplest thing over here is just nothing that 3 plus n words are required to solve this particular algorithm sum. And here C is not required. S of P is nothing but S of SP, which is SP is 3 plus n. Understanding? Any doubt? Or can anyone tell me if you have any doubt over here? Fine, I assume that you all understood. Fine. Okay. So here, this is what we have been discussing. Now, what happens is, let us talk about, see, the recursive algorithm. Here I will talk about recursive algorithm, that is algorithm R sum. The same problem, meaning you have an array A having n numbers. Okay. Here you have to find the sum of the numbers in the array. So this is the way of solving the problem recursively. Okay. Now let us talk about recursion. I'll come to recursion stack. Now what do you mean by recursion stack? See, you know function, right? Now what happens is, a function is called by a calling function. Understood? After the calling function, it goes to the call function, and the function, whatever the steps are there in the function, whatever the instructions are there in the function, it executes all those functions, right? And then what happens is it just goes back to the calling function, meaning the return address of the instruction that is to be executed just after the calling statement is stored. That is why it goes back to that calling function and executes the next instruction just after the call function statement. Understood? So that has to be stored. Now in recursion, the thing is that it does the same, but the thing is the recursion in recursion, the whole function is called again repeatedly by itself. Understood? So what happens is it needs to store the return address within a recursion stack. So recursion stack stores the return address and the formal parameters and the local parameters that is used in the function. Are you getting everyone? If anyone has a problem, kindly just
Ma'am, can you just say
yeah,
just once again?
yeah, yeah.
It's a little confusing. So
Oh, okay. For recursion stack, right? For which topic?
yes, recursion stack. Recursion.
Recursion stack. Yeah,
Yes, ma'am.
sure. Okay. See, kindly see this one. Okay. And I'll tell you again. Now what happens is in function you have to store the return address, right? Just like that, what happens is in recursion you need a stack. Why the stack? I will tell you. Here what has been written over here is I'm just writing the return address. Okay. So in recursion stack, what happens is the function calls itself again and again and again. Understood? So we just in recursion stack, what is being stored is that the return address means recursive function calls itself, right? So after the calling, something has to be done. That is why the function is called. Understood? So whatever the instructions are executed in the recursion function that is being called, it has to return back at the point where it was called in order to execute the next instruction. Understood? So we have to store the return address because it is again calling itself. What needs extra to be stored is the formal parameters, okay, and the variables, local variables that will be used in the function. Fine. Now here, just a second. Where is view? Okay, see, everyone, see this. This is algorithm R sum A n. Okay. Now here, kindly see that if n is less than equals 0, then return 0, else return R sum A n minus 1 A of n. Okay, this is the. Now let us discuss how the recursion works and how the function is evaluated. So first call is, my dear students, when you start calling. So for example, see this. Here I am taking that in AO1, okay, that is the first portion of the array. Let us assume that the array index starts from 1. Okay. Now array okay, a of 1 there is 1, a of 2 the second element we have 2, a of 3 3, a of 4 4, a of 5 equals 5, right? Now first call to the recursion will be what? As per the algorithm. What is that? Check if n is less than equal to 0. What is n over here? Can anyone tell me what is n over here according to this example? N is 5. Is it? So here, this is the recursion stack. Okay, my dear students, this is the recursion stack. And this is R sum of A of 4 plus A of 5. A of 5 is nothing but what is that according to this algorithm? A of n. A of n minus 1 is the array and 4. Right? Now I am calling the function itself. Okay, now after evaluation of this statement, it has to return. Okay, that the return address is this. My dear students, R of sum A of comma 4 plus A of 5. This is the return statement. Now in this recursive function, I am calling R of sum A comma 4. Are you getting everyone? Here, now again the function will be called. So n will be checked. N is less than equal to 0. That is a base condition. Is it true? No, it is not true. Now where it will go? It will go to else part. In else part, again you will call the function. What is that? R of sum A comma 3 plus A of n. N is what? 4 again. Are you getting? So again we have to come back and execute the return statement. So this is where this is stored again. This is the return address of the function. Okay. Now again recursively we are calling, which is what is that? This one, R of sum A of comma 3 plus A4. Now again you go to the function. What is that? If statement is checked. If statement में क्या है? If it is less than equal to 0. Is it? No. You go to the else part. Again it is called. A becomes 3 now. 4 minus 3. This is called. Then again recursively it is called. One by one it goes like that. Now when will the recursion stop? After this, after this is first, second, third, fourth, fifth call, n will be equals to what? My dear students, n will be equal to what?
0.
N will, yes, n will be 0. Now it will go to if condition. Understood? If condition, it will return what? Here the last call is R sum A and n equals what is that? 0. This is the call, right? What is the return value of R sum A comma 0? Can anyone tell me? If n is less than equal to 0, the value to be returned is what?
0.
It is there in the algorithm. 0, right? Now, see why stack is used. Why recursion stack? You see this, the call is, what is that? The call is, it starts from the first number, then it goes on. But the evaluation is done from what? The return, the function which is called at the end. That is last in, first out. So here in R sum A comma 0, the value returned will be 0. It will be added with what? Plus A of 1. So the sum is what? 1. Understood? So this total 1 is the return value of which recursive call? R sum of A comma 1. Right or wrong? Is anyone having any confusion? I repeat again, after the last call, R sum A comma 0, the return value of R sum A comma 0 is what? It's nothing but 0. Understood? So we return back to the calling function, which was nothing but r sum a comma 0. Yes, anybody? So this is nothing but what we are doing. We are returning to the call function. We need to know the return address. Understood? How the return address is being accessed. It is done by last in, first out principle. That is how the recursion is being evaluated. So here I have r sum a comma 0 equals 1. 1 plus a of 1 is nothing but 1. Now this return value is to be sent to r sum a of 1, which is 1. R sum a of 1 plus a of 2. This is the return. Here the return value will be, what is that? 1 plus 2, that is 3. So we need to know which function, which return address we have to go back to. That is to the calling function. That is nothing but r sum a of 2. Understood? Is anyone having any problem, or is the student which was asking me about recursion stack, are you getting now?
Yes, ma'am. Yes, ma'am.
Can I hear you? Are you getting now?
Yes, ma'am.
Okay, the thing is, so this is the, what is that? Actually, the call happens upward, right? And the evaluation happens downward. That is last in, first out principle. Are you getting?
Yes, ma'am.
So I will pick up one student randomly from here and ask this question on this. Is it fine? Abhijit Anand. Abhijit Anand.
Yes, ma'am.
Yes. So now let me ask you a question. Okay. So what will be the return value of r sum a of comma 3?
Ma'am, एक मिनट. R sum a comma 3.
हाँ.
Ma'am, 10.
कौन है जो बोल रहा है पीछे?
मैम वो पेरेंट्स
अरे जो
बात कर रहे हैं. Back.
ओके, क्या आप बताओ?
ये मैम R comma A3 मैम 10.
Yes, right. 10. How? Okay. Now let me ask you one more thing. Just r sum a comma 3. Okay. Plus a4 before, just after this call. Okay. Just after this recursive call, which call is met by this function?
Yes, ma'am.
R sum a comma 3 जो है, okay,
Yes,
r sum
yes.
a of 4 इस स्टेटमेंट में, इस स्टेटमेंट के बाद जो एक रिकर्सिव कॉल है ना,
Yes,
वो
ma'am.
कौन सा फंक्शन है?
मैम एक मिनट.
It is just visible in the algorithm.
मैम R A4 A3 के बाद A4 मैम.
नहीं. See, my dear student, ये in this thing, the call is, आप जो recursive है उसके बारे में आप सब भूल जाओ. इस फंक्शन में जो एक कॉल है ना, फंक्शन कॉल है ना, वो कुछ नहीं है. R sum bracket A, and the thing is the n keeps on changing, है ना. ठीक बाद जो कॉल है वो है r sum a comma 2 का. Are you getting?
Yes, ma'am.
तो आपने जो अभी r sum a comma 3 plus a4 का था, तो r sum a comma 3 को आपने कैसे इवैल्यूएट किया? R R sum a कमा 3 को आपने कैसे इवेलुएट किया?
मैम
See, my dear students, you know that you have functions where you have return values and there are functions where there are no return values, right or wrong? So the thing is, R sum a comma 3 has a return value. Okay, that is why return where in the statement also some return statement is there. Understood? Now what happens is R sum a comma 3 is calling what is that R sum a comma 2 plus a comma 5. Understood? So the return value of R sum a comma 3 is nothing but R sum a comma 2 plus a of 3. Understood? Okay, fine, fine. Let me just re remind you from the start. Okay. Now, everyone, let's start. What is that? I go on calling R sum a comma 4 plus a comma 5. Okay. Then you call what is that? R sum a comma 3, then a comma 2, a comma 1, a comma 0. From 0, you have the return value of R sum a comma 0 as 0. 0 plus a comma 1 is the return value of R sum a comma 1 plus a comma 2. Okay, this is the again added value is the return value of R sum a comma 2 plus a comma 3. Again the return value is R sum a comma 3 plus a comma 4. Then R sum finally what you have R sum a comma 4 plus a comma 5, which is nothing but 10 plus 5. Okay, which is the final thing. Now, the thing is, what happens is you go on calling the function, the return address has to be stored and it is stored in the recursion stack. That is why the recursion stack is important in recursion. Now, again, coming to my previous question, if you don't have a base, if you don't have a base condition in a recursive algorithm, will your recursion terminate or not? Will anyone tell me?
ma'am, if memory
No,
of
ma'am.
stack will be limited, then it can terminate.
Someone said no. Okay, let me tell you. So that is the thing. Okay, what happens is the recursion stack has finite. I'll give you a hint, and again you have to think. The recursion stack has finite memory. The recursion stack has finite memory.
Yes, ma'am. That's
Then will if there is again I repeat the question. If there is no this thing base condition in your recursive program, will it terminate? You store
There may be
the
stack
return
overflow.
address. Yeah, there may be that is the thing. Okay, someone is getting some idea. So what happens is it will go on running and running and running. Then finally, when the memory of the stack becomes full, you will have no more space to store the return address space for the formal parameters and parameters that is required. Understood? At that time, it will terminate for sure. Got it? Doesn't mean that it will go on infinitely. It will terminate when the recursion stack becomes full. Fine. So here we have talked about recursion. Now, can anyone tell me for this particular algorithm, recursive algorithm A, comma n, what is the depth of the recursion? Assuming that there are n numbers which to be summed up. What is the depth of the recursion means? How many recursive calls are there?
N plus 1.
Hello? Someone said
N
something.
plus 1.
Yes, n plus 1. Correct. Who was that?
Mummy Chaitanya Agrawal.
Okay, my dear students, let me tell you again. Now I said that at the mid of the class you have to the thing uh, on the right box. Sorry, on the chat box you have to write your name and the enrollment ID. Now one more correction to that. I would like you people to, when I say the class is over, I would like you only at that time to write down your name along with your enrollment ID. Okay, I repeat again. So this will be for every class. Fine. Yes, n plus 1. Very good. Now, for space complexity of this, okay, what happens is, as you have already seen the algorithm, R sum, let us kindly observe the recursive algorithm over here again. And now I've already talked about return address, right? So again, in order to simplify that, let us not assume like, okay, this return address is of type word and all. Let us assume that we just count the number of word required. Okay, let us assume that for return address only one word is required. So for R sum, as you have seen on the recursion stack, in the recursion stack, what you store is return address of one word, then the one word for storing the value of n, which keeps on changing in its recursive call, and another thing is a pointer to array of n. I repeat, for this recursive sum R sum, what you store in the recursion stack and what is needed to store for this function to work is nothing but the return address, okay, then to store one word, the value of n, which keeps on changing for its recursive call, and a pointer to array of n. So can I say that three words are needed for each recursive call in order to solve the problem? And how many times the recursion is called? That is n plus 1, nothing but depth of recursion. So finally, can I say that the space complexity is greater than equal to in the sense that there may be some temporary variable that may be needed, which is really of not important. But the minimum space requirement is that the three words into the table recursion. That is 3 into n plus 1. Okay. So this is the space complexity of the recursive algorithm R sum, which is used to find out the sum of an array of n numbers. So now here let me talk about time complexity. Okay. Now a lot of things is there in the book. As you can see again, this is what we have done. So whatever the time complexity. Now here I have given the notes point by point like this. Now let us see what time complexity means. Okay. So my dear students, what happened is time complexity. So here again, what we have to do is we have to find out how much time a particular time estimate of a particular algorithm that is being designed. Right. Now what happens is if you talk of a program, okay, running program. Now what is the time taken? If we define the time complexity again, time complexity of an algorithm is the amount of time it needs to run to completion it is the actual amount. Okay. Now, if you take that in consideration, what happens is, as you have already seen, when you run a program, first thing is that you compile a program, then you run the program. Understood? So if we talk of total time complexity, that is T of P, it is nothing but the sum of compile time and runtime. Okay. But the thing is, if we talk of compile time, it depends on the architecture of the processor being used, the compiler, everything. Okay. And the code size, all those kind of stuff. And actual thing, what happens is, if you have your COA, this is your computer architecture this semester, right? In that course, in that subject, you will see that what happens, the actual how like the instructions writing, everything happened. Now how it progressed, how it evolved, what happened is actually what your computer is doing is nothing but it is adding, it's subtracting, it's multiplication is being done, and all those kind of things. The thing is actually, again, you have to, if you are operating on a variable, what happens is you have to bring it from the memory, okay, and store it at a particular register which can be accessed by the processor. All that, those kind of things are to be considered. Okay, when actual time taken has to be calculated. So all those kind of things are really not possible, and it is actually not that required while estimating a thing. So while estimating a thing, what happens is you can just from the algorithm or from programs that you have already written, you know that there will be instructions, there are some meaningful, what is meaningful writings in your program which you can count. Okay, let's say like you can count that you are summing up two numbers, you have a statement, that statement can be counted as like one statement, those kind of things. So in order to simplify the whole thing, we define something called a program step. Program step is nothing, it is defined as a syntactically or semantically meaningful sequence of a program that has execution time, is independent, that is, and I would, ये कौन अभी ज्वाइन कर रहा है ये सृष्टि कटियार. And my dear students, today the class will go on till like 3:30, or I would like to complete some topics, okay, for time complexity, as I cannot leave it incomplete because that would not be proper, right? So now here, so I'm defining something called program step. Okay. Now program step is any step, okay, in your algorithm, in your program which has a meaningful statement. Okay, people. Now this is very interesting. Okay, you'll see some interesting stuff over here. So let me explain like how you can find out the time estimate of your algorithm in question. Okay, this is the algorithm, simple algorithm. We will count like how many steps will be there in the particular algorithm, and we can compare which two algorithm will take lesser time and which is better in terms of what is that execution time that may happen when it is converted into a program. Fine. Now, my dear students, a program step I've already defined. See a simple return statement over here. This is what is that? A program step. Then for loop, whatever, summing up, all those kind of steps. A program step. Okay. See this algorithm. Is it similar to you? Yes, it is the same iterative algorithm to find sum of array A with what is that? N numbers. So here I am introducing a variable called count. Is it visible? So after s is has been initialized to 0, I am here introducing a count variable, which is a global variable. Now, what do you mean by global variable? It is recognized all through the program, right? Just the meaning is same here in use when it is used inside an algorithm also. So it is initially zero. Count is initially zero. It is introduced, and my dear students, here again I would like to say that count is a variable introduced to count the number of steps. It is not to be counted as something related to solving the program. So syntactically, now program steps. Let me define program steps. Here, s equals 0 is a program step. The for loop is a program step. Now this s equals s plus a of I is a program step. Now return s is a program step. Okay. Why the count is introduced? Okay, fine. Let me define you what it is. And initially when I've defined an algorithm and criteria of algorithm, I have told you that we should be able to, what is that? Use a pen and paper and write down and what is that? Analyze what is happening in the algorithm. Okay. So, my dear students, if I talk of a statement count, s equals 0, 0. So can I say that the count is only 1? Now for loop you have seen, while loop you have seen, do while you have seen. For let us now try to understand how many times this for equals 1 to n will be executed. That is nothing but how many times the condition checking will be done. My dear students, for I equals 1 to n, how many times will condition checking will be done? Anybody can answer this. Or I'll randomly pick someone. Again, Siddharth 49, सिद्धार्थ सिंह, ये है कि नहीं है क्लास में? श्वेता, श्वेता चौधरी.
Yes, ma'am.
Shweta, can you hear me?
Yes, ma'am.
Okay, fine. Okay, tell me, Shweta, now according to this algorithm that is being shown on the screen, can you see it? Shweta, I can't hear you.
Yes, ma'am. Yes, ma'am. I can see it. Is it very well?
So for I equals 1 to n, so what do you think, how many times this condition checking will be done for this for loop?
Ma'am, until this condition satisfied will not satisfy.
Okay, okay, let me this thing, inform you that n equals 5.
Yes, ma'am. Okay.
Then how many times?
0, 1, 2, 3. Ma'am, 6 times.
Yes, 6 times. Meaning that, okay, for I equals 1, okay, the condition is checked whether I is less than 5, right? It is true. Then again, I is incremented, I equals 2, condition is checked whether it is less than n, that is 5. 2 times, right? I equals 3, condition is checked. Then I equals 4, I equals 5, condition is still true. Then what happens when you come out of the for loop? When I equals 6, which is greater than 5, that time it is the condition fails and it comes out of the loop. So this many times condition checking is done. That is 6 times. So now here I equals 1 to n. So how many times the condition checking will be done? Can I
And
say n plus 1?
yes, ma'am.
Right. So this again form a program step. Okay, this particular for statement is again considered a program step which is executed n plus 1 times. So the simple initialization statement that is s equals 0, it what is that? To its time complexity, it just adds just equals 1, right? For the for loop, it equals n plus 1. Now, under, if we go inside the for loop, we have a add statement that is nothing but s equals s plus a of I. How many times that statement will be executed, Sweta?
Hello? Ma'am, can you please
It's
repeat?
fine, it's fine. See, you see the algorithm again sum, okay? Inside the for loop, you have a statement that is s equals s plus a of I, right? So this statement, how many times it will be executed? It is inside the for loop.
Ma'am, n plus 1 times.
How many times?
N plus 1.
No. And plus one is when the condition fails. So once the condition fails, you will not go inside the loop. So it will be executed n times. That is n times at the times when the condition satisfies. Okay. So again,
Yes, ma'am.
here another, okay, so that you can mute your audio. So return s. This is again a program step. This will be again counted as one. Now, summing up everything, let me tell you again. The original sum algorithm is of this form. This is the original sum algorithm. Here we are talking about the time complexity is nothing but counting steps. You have to understand this step properly, how to count the steps. This is after this only you will have the asymptotic notation and comparison of time complexity of different algorithms. Please pay attention. So here, my dear students, this is a modified form of the algorithm sum. Here we are just introducing a variable count, okay, which is a global variable. Finally, when you reach the point statement number 11, you will have the final count value, which is nothing but the step count of the algorithm sum. So let us start counting again. Now that you know what is program step, okay, it is nothing but a meaningful statement in the algorithm, and comment doesn't a command is not executed. Okay, so it doesn't count as a program step. So whatever the steps, whatever the instruction in the algorithm which is executed, that has to be counted, and that is nothing but a program step. So let's start counting again. So s equals 0 0. So here count program step, counting of program step is started. So here counts becomes after this s step, this will be executed. Your count will be 1. Okay. Now for I equals 1 to n do. Now here the counting is done. This is for loop. It will be how many times it will be executed. This will be n times. Okay. Plus 1 for the last thing. Now s equals s plus a of I. Count again, this will be nothing but n times. Here, come out of the loop. This is the last time for 4. That is the plus 1. This is for return statement. That is nothing but 1. So how many will be it? So finally, can I say 1 plus twice n plus 1 plus 1? Anyone having confusion? For the S initialization, one step. For the for loop, twice n plus 1. Then inside the for loop, n, and for the return statement, 1. So how much is that? 2n plus 3. Does anyone have any confusion? This is simplified version of this. If it was used in, it was done in whiteboard or blackboard, it would have been better. Anyways, we don't have any choice. Online class. My dear students, यहाँ पे देखो, यहाँ पे for every initial value of count, okay, this. Okay, see over here, I have written something over here that will be better for you people to see. Okay, see. So here, this for count plus 1, for assignment 1, okay, 1, or C means that when like time taken is really small, in future it will be termed as constant time, okay. So those all kind of things, let's leave it like that. So for I, this thing inside n, for I equals 1, this is n plus 1. Finally, let me sum it up. This is 1, this is n plus 1, this is n. Again here written as this is 1. This is therefore the time taken, that is nothing but the program steps count is twice n plus 3 total count. Fine. Let us leave it that way. Then again we have something called the recursive sum. Again the same thing, my dear students. Okay, so let us talk about the recursive sum. Okay, in recursive sum, what happens is you have a base condition, you have a else part. Okay, so if n is equal or less to 0, then you have to return 0. So how many steps will be executed in the if block? That is the question. Now, if condition checking is if n equals 0, then this is one condition to be executed. So that is 1. Now count for the condition checking will be now what is 1. Now if the condition is true, you will go inside the loop, inside the if block. Sorry, this is not a loop. So inside the if block. So there you have a return statement. So count will be again incremented by 1. So for the if block, you have how many steps to be executed? 2. Fine. So for if block count will be executed as 2. Now let us go to the else block. Does anyone know that how many times it will be executed? We all can say is it depends on the recursive call. Okay, so the recursive call is return r sum a n minus 1 plus a of n. So you have already seen recurrence relation. So in order to represent the time complexity of recursive algorithms, we use nothing but the recurrence relation, which is in form of this. Now what it says is time complexity of the algorithm are sum with n number of input. So what it says is if n equals 0, you just execute the if block. That is one statement for condition checking of if and the return statement, which is nothing but 2. Now here, if n is greater than 0, obviously there will be the if block which will execute 2 steps. So 2 plus how many times the recursive calls will be done for n minus 1. Finally, if you solve this using repeated substitution, what happens is, so you have the tr sum n. Now this is the initial, what is that, form. Now if you again evaluate tr sum of n minus 1, it can be written in terms of n minus 2, which is nothing but 2 plus 2 plus r sum of n minus 2. Again, okay, so that is not 2 plus 2, that is 2 times of 2. Then this is being, what is that, written in this form. After that, what happens is, finally, when n, this is r, tr of sum will be 0, when n, this thing n minus n happens, that is n is less than equal to 0. So finally, that has to be done n times. So n into 2 times. So this is nothing but twice n. So tr of sum of 0 according to the recurrence relation, what is that? If n equals 0, the value is 2. So this is substituted over tr sum equals 0. So finally what you have, 2 twice n plus 2. This is the step count of recursive sum. Now compared to the iterative algorithm, the step count was twice n plus 3, right? Now what we can say over here is that the time complexity of recursive algorithm of the summing of n numbers is less than the time complexity of the iterative algorithm, right? So this is how we analyze space complexity and time complexity of algorithm. Okay, everyone post your name along with your enrollment ID in the chat box. And anyone having any question, please ask. Vivan,
Yes, ma'am.
unmute your audio.
Yes, ma'am.
So can I ask you something?
Yes, ma'am. I'll try.
So now that we have concluded, we have come to the conclusion that the time complexity of R sum is twice n plus 2, right?
Yes, ma'am.
So but here we say that when n is less than equal to 0, it is the it is having the value of 2, the time complexity. So
Yes,
how
ma'am.
is it having the value of
How? Once
yeah
will be for checking for the for condition. I mean the if condition,
for yeah yeah yeah
and the second time will be
and
for checking the conditional return. Return statement
Then
for
it's a
return statement.
statement.
Return statement.
Yeah. Then okay. For n greater than zero, what happens in this algorithm?
There'll be recursion. We'll go to recur. We'll check the if condition and then return to the
Hmm.
recursive statement.
Okay. So how many times the recursive call happens? It will contribute. The time complexity will depend on that. Is it?
Yes, ma'am. Yes, ma'am.
Okay. Can you just see the recurrence relation and the solving of it? This is done by substitution method, right?
Hmm.
Okay. Now at the final statement, the time complexity of R sum of zero. Okay.
Yes, ma'am.
How we got the zero over here?
Uh, I don't know how to explain it, but as we keep on substituting, then eventually
Hmm.
the term within the parenthesis n minus 2 that will keep on increasing and it will become n minus n. That will
Right.
be
N minus
0.
n. It's a right, right. It is a time when you reach the base condition of the recursive algorithm. Understood?
Yes,
Are
ma'am.
you getting? Base condition of
Yes,
the
yes.
recursive algorithm. That is where you check the if block. Okay. So for the
Mm,
if block, you check the condition and you go inside the if block. For this particular algorithm, you have only the return statement. So that is why the program one plus the condition checking if. So it's total is two. Understood? So that
mm,
so please keep in mind that it is where you reach the what is that base condition of the termination of the recursive algorithm. Okay.
yes, ma'am. Mm.
Okay, fine. Anything you want to ask?
Not particularly, just I'll have to revise once again. And
Okay, fine, fine, fine. Okay, fine. Anybody having any question? Okay, let us end today's section now. Thank you all.